Okay, so the AP exam, AP statistics exam generally comes in two parts. There is 2 hours worth of multiple choice and 2 hours for the free response questions. The free response questions, generally there are 4 to 5 to 6 of them. The last one being substantially longer with parts A, B, C, D, E, F, and so on. It's substantially more difficult and is expected to take you a good 20 minutes, a good portion of the 2 hours for the free response questions will be spent on that last question. It's not a question you can really study for. They're really good at giving you a new type of graph you've never seen before and seeing how you can interpret that. So it's the more challenging of the questions. Okay, so this video will go through a number of free response questions that were actually on the 2019 exam.
All right, number one, the size in square feet of 20 rooms in a student resident hall in a certain university are summarized by the following histogram. Part A, based on the histogram, write a few sentences describing the distribution of room sizes in the residence hall. Remember that when describing distributions, you must use this acronym SOX. SOX stands for well, in no particular order, I'll say shape, outliers, center, and spread. Make sure you might even add another C to that you talk about context. So don't just say the median is 10. You need to talk about what the median of what, right? So use context in all of this. Make sure too that if they ask us to compare to different distributions, that you're not just listing what the things are, but say the men's foot size is larger than the women's foot size is, as seen by the median or whatever. So use full sentences, use comparing words, but list the actual values if they ask us to do two. In this case, they're just asking us to do one. So describe that, use SOX, but also include context. All right, so the shape is bimodal, it has two peaks a little bit there. It's fairly symmetrical. There do not appear from just looking at the distribution that there are probably any outliers. They're going to ask us to check that in a minute. The center, you could either say the mean or the medians. Since they're symmetrical, the mean and the medians are both pretty much in the middle. So either one of those would work. And the best we can say is that the mean or median is between 200 and 250 square feet. So remember that use context, right? So the median size of the rooms appears to be between 200 and 250 square feet would be good. The spread, now remember the spread. Range is the best thing to use here. Do not say that the range in student room sizes is 100 to 350. That's not right. Remember, the range is the maximum value minus the minimum value. And, we don't really know exactly what the max is. It's probably not 350, but it's probably not 300. So, if you said about 350 minus 100 is about 250, that would be appropriate. And about is about all we can do. All right, part B, summary statistics for the sizes are given in the following table. Determine whether there are potential outliers in the data. Now they're wonderful about asking questions that require you to know the formulas and be able to use the formulas rather than using just putting the data into your calculator. So often if we were interested in figuring out whether we had an outlier, we would put the data set into our calculators. We would run we would plot a modified box plot, and then the little dots would show up and indicate to us that we had outliers. But in this case, they did not give us the data. So you have to use the formulas. You must be comfortable with how to use the formulas because your calculator will not always help you. They're infamous, the College Board, at writing these exams so that you cannot necessarily use your calculator all the time. Okay, so the first thing we want to do is calculate 1.5 times the IQR. Remember that the IQR is Q3 minus Q1. So they gave us Q3, they gave us Q1, we can subtract those. So we subtract those, we multiply that difference by 1.5, and we get a 1.5 IQR of 177. Now 177 is now sort of our measuring stick. There are going to be outliers if there's any room size that is 177 below Q1. Well, obviously that's not possible because Q1 is 174, and that would give us a negative room size, which is not possible. So we know at this point there are no outliers on the lower end, even without looking at the minimum, but the minimum is 134. So clearly there are no outliers on the low end. All right, and then the upper end, if we have any room sizes that are 177 square feet above Q3, and we can see the maximum is 315. So clearly, if we had any room sizes above 469, then those would be outliers. So clearly we have no outliers. All right, so no outliers. Now, if we had looked at part C, here they're asking us, not part C, sorry, part B. They're asking us to create a grid or a box plot using this grid, using the room sizes. So since they're asking us to do a box plot without the actual data, we should have been suspicious. We should have kind of known that there were not going to be any outliers. Because let's say that 315, let's just say that 315 had been an outlier. Well, the whisker would not go out to that 315. Instead, it would go back to the next non-outlier data value, which would be impossible because we don't know what those data values are. So even, before we calculated whether, the 1.5 IQR, we should have probably been able to figure out from what the information they gave us, there could not have been any outliers. We would not be able to been able to graph the box plot properly if there had been any outliers. Okay, so how do we do a box plot? So remember, we can't do this on our calculators. We have to be able to do this by hand. All right, so we look at the minimum, we plot the maximum, we do Q1, we do Q3, and we do the median, and then we draw those in. Now, sometimes we don't do the vertical lines at the min and the max. Sometimes it's just the whisker going out to it, and then we don't put the vertical line. Two different ways of actually doing it. All right, now part C for this first problem. I have both of the graphs here. What characteristic of the shape of the distribution of room sizes is apparent from the histogram, but not from the box plot? Okay, so clearly we can see that it's bimodal. We cannot tell that it is bimodal looking at the box plot. We can't really see that there's very few rooms, actually just one room, that is room size between 200 and 250 square feet. That is absolutely unapparent in the box plot. Okay. Okay, number 2, researchers are investigating the effectiveness of using fungus to control the spread of an insect that destroys trees. The researchers will create 4 different concentrations of fungus mixtures: 0 milliliters per liter, 1.25 milliliters per liter, 2.5 milliliters per liter, and 3.75 milliliters per liter. An equal number of insects will be placed into 20 individual containers. The group of insects in each container will be sprayed with one of the 4 mixtures, and the researchers will record the number of insects that are still alive in each container 1 week after spraying. Part A, identify the treatments, experimental units, and response variable of the experiment. Okay, the treatment are going to be, there's 4 different treatments or 4 levels of the one explanatory variable. So since we're using just the one fungus, there's really just one explanatory variable. If we were using different types of fungi, then we'd have multiple explanatory variables. But in this case, we're using the same fungus, but just 4 levels of it. So one explanatory variable, even though they weren't explicitly asking about that, there are 4 treatment groups. Each group corresponds to one of the 4 levels of the explanatory variable. All right, the experimental units are not the individual bugs. The experimental units are the 20 containers, each containing the same number of bugs. So each one of those is an experimental unit because each one of those is going to be randomly assigned a treatment. All right, the response is the number of live insects in each container at the end of 1 week. Part B, does the experiment have a control group? Explain your answer. Clearly, yes, it does have a control group. Each container is going to be sprayed with one of the 4 solutions. The control group in this case is the one that has 0 concentration, 0 milliliters per liter, or just water. The control group's important here because maybe, I don't know, maybe just putting the insects in the containers tends to kill them, right? So maybe it's being contained within a container that will kill some bugs. So the control group will allow us to see, well, what happens to bugs that aren't sprayed with anything but are just in the container. All right, part C. Describe how the treatments can be randomly assigned to the experimental units so that each treatment has the same number of units. All right, so this is where you would want to go into detail about how you might use a random digit table and explain in detail how you would assign each treatment to each randomly assigned group. All right, so first we're going to number the containers, not 1 to 20, but 0, 1 to 20, because we want to think about using 2 digits at a time there. We're going to start on a particular row. I chose 107, but you can choose any row on the random digit table. You're going to find 5 distinct 2-digit numbers in the range of 0, 1 to 20. You will ignore repeats and numbers from 21 through 99 and 00. You could have numbered the containers 00 to 19. That you could have done that as well. You just need 20 2-digit numbers. All right. The containers with the corresponding 5 numbers will be considered treatment group 1. We will give them 0 concentration. We would repeat steps 3 and do that for group 2. So we would look for 5 more 2-digit numbers, ignoring any numbers that we had chosen before, and also any numbers between 21 and 99 and 00 again. And then we do that again for group 3, for treatment group 3. And then finally, the numbers that are left, whatever containers that weren't chosen for the first 3 groups, those by default will be in treatment group 4. You do not need to randomly choose those last 5 containers for group 4. All right, number 3. A medical researcher surveyed a large group of men and women about whether they take medicine as prescribed. The responses were categorized as never, sometimes, or always. The relative frequency of each category is shown in the table. So they broke each response up according to whether it was from a man or a woman and whether their response was never, sometimes, and always. And all that is shown here in the table. Part A. One person from those surveyed will be selected at random. Number 1, what is the probability that the person selected will be someone whose response is never and who is a woman? All right, so we want probability of never and a woman or intersection. And so we want to look at those two, that column and that row, and where do the column and the row intersect. And so that's simply the cell where the column and the column and the row intersect, and that is about 6%. All right, number 2. What is the probability that the person selected will be someone whose response is never, or who is a woman? All right, so we can use the symbol union or to represent this, so that we want the probability of that the response is never, or that the response is a woman. So we think of it as or, meaning addition. So we want the probability of never plus the probability of a woman, but we need to also subtract away the probability that they're both. So in other words, if we just simply add up the column never and use 12%, and we add to that the row 53%, problem is we've counted the intersection, about 6%, we've counted that twice. We counted it in the row and we counted it in the column, so we would need to subtract that away. So that gives us about 59% as a result. All right, 3. What is the probability that the person selected will be someone whose response is never, given that the person is a woman? So be careful, this is definitely a conditional probability here. All right, so remember we use the vertical slash to indicate given that. So the probability that the response is never, given that it's a woman. So we know we're in this row, and so we simply look at that 6% divided by the 53%, or about 12%. All right, part B. For the people surveyed, are the events of being a person who responds is never and being a woman independent? Justify your answer. All right, so remember that in general, for independence of two events, let's just call them in this case A and B, that means the probability of A is equal to the probability of A given B. So given that B happens, the probability that A happens will be the same as if probability of A happens just by itself. So in our case, when they ask these questions, invariably they're asking us using the probabilities that we were just calculating in the previous parts. So we know that the probability of never is 12%, and the probability of never, given that you're a woman, is about 12%. We saw that last calculation. So this means that the response never and being a woman are indeed independent, because probability of never and the probability of never, given that you're a woman, are both 12%. All right, part C. Assume that in a large population, the probability that a person will always take medicine as prescribed is 54%. If 5 people are selected at random from the population, what is the probability that at least 4 of the people selected will always take medicine as prescribed? Support your answer. So you want to think about what type of probability distribution applies in this situation. Okay, so I think binomial will apply. Let's check our for condition, or bins, to see if this works. So the success or failure for each person, right? There's going to be the success. They take their prescription as subscribed, or they don't, their medicine as prescribed. The next one is each one is going to be independent of each other. That makes sense. And our 10% rule, right? We have assumed that there's more than 50% in the population, 50 persons in the population. And there's a set number of trials. We are randomly selecting 5 people, so each person is an independent trial. And then the probability of success is the same always, especially since we're not sampling more than 10%. The population proportion of people who take their medicine is going to be consistent. It's going to be 54%. All right, so this is clearly a binomial situation. Remember to think back when we did these, we kind of did 3 steps. We talked about what kind of distribution. We defined a random variable. We said what kind of distribution it had. We did the calculation, and then we actually answered the question. All right, so I let X be the number of successes in 5 trials. That will be our random variable. It has a binomial distribution. Key values are n equals 5, the set number of trials, and the probability of success for each trial is 54%. We're going to sometimes list down what it is we want to calculate. We want to calculate the probability that we have 4 or more people, at least 4, so 4 or more. So if we calculate this in our calculators, remember the binomial CDF will calculate the probability for a particular value and all the values below it. So we want to use, we would have to use 3. Remember too that this is not a continuous random variable, it's a discrete random variable. So there is a difference between the probability that X is less than or equal to 3 and the probability that X is less than 3. There's a big difference there, unlike when we talked about continuous random variables under a density curve. More often than not, a normal curve, the difference between those two is nothing. There's no difference between them. But here, there is a big difference. So we want to include 3 in our calculation. So it's a binomial CDF with sample size 5, probability of success 54%, and X being 3. So that will give us the value, the probability that you would have 3 or less successes out of 5, and then we will subtract that from 1 to get the probability of 4 or more. So it's about 24%, and then simply we state that in a sentence. If the probability of a person always responding always is 54%, then the probability of at least 4 out of 5 randomly selected people responding always is about 24%. All right, number 4, tumbleweed. Commonly found in the western United States is the dried structure of a certain plant that are blown by the wind. I don't know, kochia, I guess. Kochia, a type of plant that turns into tumbleweed at the end of the summer, is a problem for farmers because it takes nutrients away from the soil that would otherwise go to more beneficial plants. Scientists are concerned that kochia plants are sometimes resistant to the most common used herbicide, glyphosate. We'll call it glyphosate. In 2014, 19.7% of 61 randomly selected kochia plants were resistant to the herbicide. In 2017, 38.5% of the 54 randomly selected kochia plants were resistant to the herbicide. Do the data provide convincing statistical evidence at a level of alpha of 0.05 that there has been an increase in the proportion of all kochia plants that are resistant to the herbicide? This is clearly going to be a 4-step problem, so make sure that you're using your 4 steps. Think about what inference procedure we're talking about here. Are we dealing with significance test? Are we dealing with confidence intervals? Are we dealing with means? Are we dealing with proportions? Are we dealing with difference of means? Are we dealing with difference of proportions? All right, so we're using our 4-step process here. The state. So this is going to be a hypothesis test for difference in proportions. So I'm calling the 2 proportions with subscript 17 and 14 to keep track of them. You can just use P sub 1, P sub 2. Remember, those P's represent the population the proportion in the population that are resistant to the herbicide in each of the years. Now, our hypothesis test is saying that there is no difference between the two. So we could say that the difference between them is equal to 0, or we could say that P sub 17 is equal to P sub 14. Either way you want to do that, but be consistent. All right, so the alternative will be that it is greater than, because we're testing whether or not whether there has been an increase in the proportion that are resistant. So we're thinking as the alternative that the proportion in 2017 is not just by random chance, that it's actually, that we saw is not that just by random chance, but it is actually higher in the proportion of resistant plants is higher in 2017. So I put 2017 first. That way, when I subtract 2014 from it, I should, as the alternative hypothesis, get something that is greater than 0. So be cognizant of which order you're putting those in, because if you flip those, you're going to have to say it's less than 0, which seems a little weird because we're saying that the proportion increases, but yet we're saying in the alternative that it's negative. You can still do that, but just be cognizant of which way you're doing that. All right, now we have to explain what P hat sub 11 and P hat 17 and P hat of sub 14 are. They are the true population proportion of cochea plants that are resistant to the herbicide in the years 2017 and 2014 respectively. And the third thing, make sure that you say what alpha level you're using. All right, the plan now. All right, the plan, we're doing a z-test for difference in population proportions if the conditions are met. So 3 conditions. Both samples were randomly selected. So don't just say random sample. You have to make sure that you're talking that both samples were randomly selected, that we are talking about 2 separate independent samples and that they were both randomly selected. All right, verify that we did not sample more than 10% from each of those populations. So in 2014, we would have to make sure that we know that there are more than 610. And then 2017, we have to make sure there's more than 520 of those plants. All right, part 3 is the more tedious one. You have to check all 4 large count conditions, the number of expected successes and failures in each of the samples. So N sub 14 times P hat sub 14, N sub 14 times 1 minus P hat sub 14, N sub 17, P hat sub 17, and N sub 17 times 1 minus P hat sub 17. So all 4 of those you need to check and verify that all of them are bigger than 10%. Okay, if you're doing this by hand now, the do part, we have to pool the data. Your calculator, if you're using your calculator, which I'll show in a second, your calculator knows to pool the data and automatically does it for you. So if they're giving you a question, and they're notorious about giving you questions that you have to do by hand, so you know the calculator, the calculations. This is the one situation, difference in proportions significance test, that we have to pool the data. So it's the number of successes. It's that 12 plus the 20, the red numbers up above, divided by the sample sizes total. And that gives us about 28%. That is the P hat value that is used to calculate the standard error in the denominator of our Z statistic. Okay, so we do 28% and then 1 minus 28%, the 71.7%. All right, so that gives us our Z score of 2.2. We go to our table and we look for the probability that the Z is bigger than 2.21, and that gives us about 1%. It's a p-value. If we do this using our TI-84s, it's a 2 proportion Z test. I remember a number of kids last year came back after the exam and said that they had problems. Their calculator was giving them errors, and it was this problem, I'm sure, that was doing it. Because if you And notice in the problem up above, they gave us percentages. So we had to calculate that 12 and that 20, the number of successes in each sample, those must be integers. So if I rounded my 20, or my 12 and my 20 to the nearest 10th place, but if I had gone out to another decimal place, it would not have been 0. And if I had tried to enter those into my x sub 1 and x sub 2, my calculator gives me domain errors. So you cannot, just make sure that your x values and your n values must all be integers, which makes sense in the real world. They would be integers, but when you work backwards from the p hats that they gave us in the problem, then often we would look at those as being approximate, which don't make any sense. I mean, those would have to be actual integers. And so you must enter those as integers. All right, also be careful about the order in which you're putting these things. So I'm using p sub 1 as my 2017 and my P2 as 2014. I'm just following the same order that I set up as my alternative. If you reverse those, it's not a huge issue, but what will happen is that your z-score will be negative. And then that might cause you confusion and you might be looking at it the wrong way. So you reverse the inequality, and if you revert and or reverse the which one is P1 and P2, then you're going to get some errors. So be careful about that. All right, so it gives us our p-value of about 1% as well. And so finally, the conclusion. Oh, don't forget that you have to include your z-score. Now, this year's test is going to be on the computer. You probably won't be required to put a z distribution, a normal curve with shading on it. You'll be forgiven for not doing that, I'm sure. All right, so the conclusion now. Remember, our conclusion always has 3 parts. To a hypothesis test, we compare our p-value to our alpha. So our p-value is less than alpha. It's not a good idea to include the actual values there. Therefore, we're going to reject H naught. And then we have convincing evidence that the population proportion of herbicide-resistant Kochia plants has increased. Now, be careful. Some of you in the last test, when you were doing your conclusion, you would say things like, we have convincing evidence to conclude that the proportion is. So it's a very definitive statement if you say we can conclude. It's almost akin to saying that we've proven it to be true. So just stay away from anything that sounds like we know for sure that the population population proportion of herbicide-resistant plants has increased. We don't know for sure. We have strong evidence to support it, and that's all we really want to say. So we just say we have convincing evidence that the population proportion of herbicide-resistant plants has increased. That's all we can say. Don't say anything that sounds more definitive, that we're certain, that we are going to conclude that that's true, that kind of thing. So just say we have convincing evidence. All right, number 5. A company that manufactures smartphones developed a new battery that has longer lifespan than that of the traditional battery. From the date of purchase of a smartphone, the distribution of the lifespan of the new battery is approximately normal, with mean of 30 months and a standard deviation of 8 months. For the price of $50, the company offers a 2-year warranty on the new battery for customers who purchase a smartphone. The warranty guarantees that the smartphone will be replaced at no cost to the consumer if the battery no longer works within 24 months from the date of purchase. All right, part A. In how many months from the date of purchase is it expected that 25% of the batteries will no longer work? Justify your answer. Okay, so we know that we're dealing with something like this normal curve, and you know, 25% will be on the left side of it, right? Because at some point where the blue vertical line is, the battery stops working. So how many will stop at that point? So we're going to use this is the reverse sort of our z-score. We look at our area in our table, and we get a z-score from our table of about negative 0.675. We can un-z that using our z-score calculation and solve it for x, and that gives us about 24.6 months. If you're using your calculator to do this, you would go and you would look at your inverse norm. You would put your area in on the left. That's always the area on the left. It's 25% or 0.25. The mean is the mean that they gave us of 30 months and the sigma of 8 months. And we would paste that in, and that would give us 24.6 months directly using our calculator. If you're going to use your calculator, then I would explain, type out whatever it is that you did on your calculator, say what test you used, or in this case, what distribution you used, and explain that entirely, and what values you plugged in and all that to get full credit. All right, part B. Suppose one customer who purchases a warranty is selected at random. What's the probability that the customer selected will require a replacement within 24 months from the date of purchase because the battery no longer works? All right, so we want to look at what kind of a z-score this is. So this is below the mean, of course. 24 months is below the 30 months, so it makes sense that our z-score is negative. Similar drawing to what we had before. In this case, the z-score is about 3/4 of a standard deviation. And now we want to go backwards from what we did in part A, and we want to find the area. So we can certainly go to our z-score table and look up a z value of negative 0.75 to get that area. We can also use our calculator, our TI-84. And again, we would simply look and use the normal CDF this time. And we would look at a very low number for the low, the upper value of 24, and put in the mean and the standard deviation. Again, gives us 22.66. Probably good, since they're asking us for a probability, to go ahead and answer the question in a full sentence. All right, so there's about 23% probability that the randomly selected customer will require a replacement battery within 24 months of the purchase date. All right, part C. The company has a gain of $50 for each customer who purchases a warranty but does not require a replacement. So they charge $50 for each warranty. For the people who actually need a new battery because it has stopped working within 24 months, of course, the company is going to lose money. So the company has a loss or a negative gain of $150 for each customer who purchases a warranty and does require a replacement. So we are going to assume that the phone that gets replaced could have been sold by the company for $200, but since they already made up $50 from the person, that they're losing 150. So you don't have to worry about taking the difference in those numbers. They've already given us the fact that the company is losing $150 every time you get to replace your phone because it's stopped working, and they gain $50 every time a customer doesn't replace a phone because it has not stopped working within 24 months. All right, what is the expected value of the gain for the company for each warranty purchased? Okay, so we can think of it as a probability distribution in a table, right? There's two possibilities. The company gains $50. That's for people who do not require a replacement phone. And they lose $150. That's for the people who do require a replacement phone within 24 months. All right, so we saw in the previous part in problem 5B that we know that 22.66% of the batteries are expected to fail within 24 months of use. These failed batteries will cost the company $150. So that's the probability that goes under the gain of negative $150. All right, so clearly the rest of them have to be 77.34%. All right, so calculate the expected gain for the company. Remember, we simply multiply each gain times its respective probability, and then we sum those up. So the company is expected to gain about $4.68 from each, and of course we just want to state that in a sentence.